Okay, to start part 2 of homework 7-4, we'll pick up with question 7. And question 7 at first looks a lot like we're going to have to set up a system of equations. Actually, though, is a little bit easier than that. This one, because of the information they give us, actually gives us a route to solve this without having to do a full system here. But anyway, I'll give you guys, obviously, hopefully you've read through this a little bit here. But as you read through, they give us a lot of information about how far that block has fallen, right? So we know it starts at rest, the system starts at rest, which tells me the initial velocity, the initial linear velocity, would be 0. I know the delta x, the displacement that it falls, is 1.5 meters, and it does so in a time of 2 seconds, right? So again, once you get those 3 pieces of information, hopefully this is jumping out from stuff we've done all year, right? That, hey, we can do some kinematics and we can find either the acceleration or the final velocity if either of those would be helpful. And in this case, it is helpful to go ahead and find the linear acceleration, the tangential, I should say, acceleration. Right, so I'm going to use some linear kinematics to find the tangential acceleration. So using my delta x equals v sub 0t plus 1/2 at squared, much like we did in the last question as well. I know this is 1.5. My initial velocity, again, being 0, simplifies it a little bit here for me, and then 1/2 the acceleration times 2. So this actually works out very nicely. 2 squared is just 4, half of that is 2. So then 1.5 divided by 2, we don't need a calculator for that, right? Which is 0.75 meters per second squared. So again, keep in mind this represents the tangent acceleration, right? This is how fast the block is accelerating tangent to the circle. So then how can I use that to help me with the rotational motion? Well, that can obviously help me find the alpha, right? The angular acceleration would be related using the tangent. So the tangent equals r, the radius, times the angular acceleration. So since I have the tangential acceleration, 0.75 equals my radius of 0.40 meters, which they give me, and then my alpha there. So solving for alpha, I get alpha to be 1.875 radians per second squared. So we do have this information to work with, which obviously helps me out for this problem. They're asking for the moment of inertia of the wheel. And so, much like we did again in question 6, we're going to take advantage of the net torque for the wheel equals the moment of inertia times alpha, right? So I just found my alpha. So now the question becomes, can I find the net torque on the system? Well, this one's really nice because obviously if I look at finding the net torque, they flat out in the question, they flat out tell me the tension, right? And since I know the tension and I know the radius, and it doesn't say that there's any other forces or torques acting on this system, right? We'll assume that it's a frictionless wheel. In fact, they tell us there's frictionless bearings there. So that is the only torque acting on the system. And to find the torque, it's just the force times the radius. So in this case, the force would be my tension times the radius. So since they just give me the tension, they don't ask us to set up a system to calculate it. They give me that tension 20. Then I know that my net torque is just 20 times the radius of 0.4. So obviously that ends up being 8 when we calculate that, 8 newtons meters, right? So that is the net torque on the system. I've got my alpha. Bring that all together to find my moment of inertia is as easy as plugging those measurements in. So my net torque of 8 newton meters equals the moment of inertia times my alpha, my angular acceleration of 1.875, and then again solving for the moment of inertia, 4.27 kilograms times meters squared, right? So there's my moment of inertia for this disk. Again, a little bit easier because I didn't have to set up a full system of equations to get there. Okay, so question 8 is very similar to a question we used to do. However, it is one question we have to be careful about. So we've got a ramp and then we've got a cylinder. It does tell us it's a cylindrical shell, so a thin cylindrical shell. So basically it's going to be acting like a thin hoop for us, right? So it's got just the shell of a cylinder, but the inside is hollow here. So it's going to be acting like a hoop. So then the misconception here, what we have to be careful about is, in the past when we didn't have an object rotating, so when it was just sliding down the ramp, what you actually could do is you could say that the acceleration of 9.8 pulling straight down, and then the component of that going down the ramp, and then once we find the component of the acceleration down the ramp, we could just do kinematics. The problem is, because this object is also going to have a rotational kinetic energy, the acceleration can't quite be simplified that much, right? Some of the acceleration is going to cause it to turn, and some of the acceleration is going to cause it to go down linearly. So we have to be very, very careful with that. So instead, what I would recommend is using energy as much as we do for these types of problems when we know when it's rolling down a ramp, right? And so what I mean by that is we know we start with a potential energy and we convert that to both a rotational and a translational kinetic energy, right? Linear kinetic energy. So much as we've seen a few times now, I'm just going to break this up in terms of the measurements we know, right? And then I'm going to try to represent these all in terms of the same variable. So I'm going to break up the moment of inertia and omega in terms of m and v and r and all that fun stuff, right? So I get mgh equals 1/2. Keep in mind, for a cylindrical shell, it's a little misleading here because you think maybe a cylinder, but it's really going to act more like a hoop because it's just the thin outer shell of that, right? So that makes this just mr squared, and then again omega would be v squared over r squared once I square that, so the r's can cancel out nicely, and then plus 1/2 mv squared. So at this point I have mgh equals 1/2 mv squared plus another 1/2 mv squared, right? That is an h over here, by the way. But anyway, so I've got that set up, and then obviously the mass doesn't really make a difference, so we can divide everything by the mass and get rid of that. So then looking at this point, I really have the acceleration of gravity times my height, and then that can help me find the final velocity after this distance of 3.1. So that's what I'm going to do, is I'm going to find my final velocity, and then using the final velocity, I'll just do some kinematics to help me find out the time that it takes. So from this point, the acceleration of 9.8, the height, well, it tells us it goes 3.1 meters down the ramp. So then to find height, I would just take that times the sine of the angle that they give me. Right? This is representing the height of the ramp here. And then 1/2 again, velocity squared, plus another 1/2 the velocity squared. So 1/2 plus 1/2 is obviously equal to 1 v squared. So really just 9.8 times 3.1 times sine of 30, and then the square root of that. When I do that, I get the velocity to be about 3.90 meters per second if I round it off to a couple decimal places there. So 3.90 meters per second. That's my final velocity after this object has rolled 3.1 meters down the ramp. That obviously does not answer my question yet, though. They do ask me how long does it take, right? So then from here, all I have to do is try and find my time, right? So that's going to be my goal. So anyway, we're going to try and find then our time, right? That's our goal. So now that I have the final velocity, I know the initial velocity would be 0. I know the distance, the delta x, would be 3.1, and again, I'm looking for my time. So probably most of us would want to do that through a couple equations, right? We could use v squared equals v sub 0 squared plus 2a delta x to find the acceleration. And when I do that, I'll trust that you guys can plug in the numbers here, right? When I do that, I find the acceleration should be about 4.91 meters per second squared. So I've got my acceleration again resulting from this, and then once I have the acceleration, if I just want to use any of the equations, really, I could use either delta x, or I can use VOTAT, right? V, the final velocity equals the initial velocity plus a times t. Whichever equation I want to use, ultimately both of them should work out to be about 1.12 seconds is how long it takes to roll down the ramp. Right? So again, be careful not to just use the acceleration, because it's not just the same component of the acceleration. We actually have to use energies to find the final velocity, and then do some kinematics from it. So then question 9. Question 9 at first looks like it's going to be pretty intimidating because they give us these 5 parts. If you actually take it one step at a time, I think this, hopefully you guys would agree, maybe one of the easier questions on the homework. So for part A, they say calculate the linear speed of the center of the sphere when it reaches the bottom of the incline. Well, again, that's the same type of relationship we've seen a few times now. At the top, we know it starts with potential energy. By the time it reaches the bottom, it has both rotational and linear kinetic energy, right? So all I have to do then is break this up and then represent it in terms of the linear velocity, so v, and then solve from there. So if I break this up, well, obviously the potential energy is mg times h, and they tell us all that fun stuff to work with. And then here rotationally it'd be 1/2 the moment of inertia. Well, for a sphere the moment of inertia is 2/5 mr squared. And then again, representing, instead of 1/2 the moment of inertia times omega squared, I'm going to represent omega as v squared over r squared, right? So I'm going to represent that quantity as v squared over r squared, which helps me to cancel out the radius, so I don't need the radius, and then it represents it in terms of just the linear velocity instead of the angular velocity. So this whole mess represents my rotational kinetic energy, and then my translational kinetic energy would just be 1/2 and then mv squared. So I've got that to work with as well. So then if I look at this equation, again, not only was I able to cancel out the radius, but if I look at this relationship now, the potential energy and both forms of kinetic energy all depend on the same mass. So if I divide everything by that same mass, I actually can drop that out of the equation too. So I get g times h equals 1/5. If I do 1/2 times 2/5, it's 1/5, and then v squared, and then plus 1/2 v squared. Right? So at this point, it makes it very clear to see my linear velocity, my velocity, which is v, is going to relate solely to the height and the acceleration due to gravity. Right? So that actually helps me then answer part D. Does the linear speed in A, does our linear velocity here depend on the radius or the mass? No, it doesn't, right? I can get this same velocity no matter what the mass, no matter what the radius. The only thing that really is important is what is the height and what is the shape, right? Because the shape is going to affect what coefficient I use down here. So the shape and the height are the only two really independent variables, if you will, for that final velocity. So for part D, I can already answer that that is a no. So then again, from here, just calculating this, 9.8 times the height, which would be 7 times the sine of 35, right? It's just the vertical portion of that inclined plane. And then if I look at this, 1/5 plus 1/5 plus 1/2 would be 7/10 v squared if I get a common denominator there. So then solving for v, right, just solving for the velocity, I end up getting that the velocity is about 7.50 meters per second. So the answer for part A, 7.50 meters per second. So I killed two birds with one stone there. I got A and D already taken care of. So then for part B, well, for part B, determine the angular speed of the sphere about the center at the bottom of the incline. Don't make this worse than it has to be, right? Don't think we have to, again, reinvent the wheel here. No pun intended, right? But we don't have to reset everything. Instead, for part B, once I know the linear velocity at the bottom, isn't the linear velocity of the center of mass just going to relate to the radius times the angular velocity, as we've seen before, right? So the linear velocity of 7.50 is going to equal the radius, which they give me. The diameter is 30 centimeters, so the radius would be 0.15 meters, and then the angular velocity is what I'm solving for. So when I solve for the angular velocity, right, just dividing by 0.15, and I get that that is 50 radians per second. So the angular velocity is 50 radians per second. But anyway, so I've got those two measurements. Answering part E, since I've just answered that, right? Answering part E, does the angular speed depend on the radius or the mass? Well, yes, it does, right? What measurement did affect the angular velocity? And it was radius, right? Depending on what the radius is, we know that it has a linear velocity of 7.5. So depending on what the radius is going to depend on how fast the angular velocity had to be to compensate for that. So yes, it does depend on the radius. It does not, however, depend on the mass, right? It does not depend on the mass. So we've answered part B and E in the same below. So then my final question is, right, through what angle in radians does the sphere turn as it rolls down the incline? Right, so through what angle in radians does it turn through as it rolls down the incline? Well, for part C, again, you could do a couple different things. You could do some angular kinematics. You could say that it starts at rest, you know how far it goes, all that fun stuff. But honestly, if we know that the ball is rolling, or if the sphere is rolling down the incline, then as it rolls, isn't its circumference going to translate to the linear distance down the ramp that it goes? So what I mean by that is, however far it goes down the ramp, which they told me was 7 meters, isn't that 7 meters going to represent the linear distance around the circumference that it's traveled? So in other words, that x is going to be the arc length around the circumference that we've traveled. So that 7 meters is my arc length. Well, what's the relationship between the arc length and the angle measurement in terms of radians? Well, it's the arc length, that linear distance or displacement, is just going to be the radius times the angular one. So again, once I have my 7 meters down the ramp, I just am going to take the radius of 0.15 times theta, and I'm going to divide both sides by 0.15. So my theta in terms of radians ends up being about 46.6 repeating, so 46.67 if we want to round that off. But that's how many radians the sphere turns through as it rolls that far down the ramp. Okay, so again, don't make that more complicated than it has to be. However far down the ramp it's gone, that is the arc length around the circumference that the sphere will also have had to have rotated through. So then I just need to convert the arc length to the angular displacement.